Good day, students. Today we have the principles of measurements for our topic. So this is particularly important because it will help us ensure that the generated laboratory data are accurate and conform to the quality standards. First, for our learning objectives. At the end of this lesson, you're all expected to differentiate sensitivity and specificity. Differentiate accuracy and precision. Next, determine the reference ranges of samples based on the given data. And lastly, familiarize the process of method selection, evaluation, and monitoring. First, let's have this table. So this table shows the actual results of the patient, or let's say the diagnosis of the patient, and of course the predicted result of the patient. So this one is the one that is released in the laboratory. So first, let's have true positive. So what does it mean when we say true positive? So it means the number of patients that were tested positive and were actually positive for the disease. So in short, you are diagnosed with a particular disease and the laboratory results also suggest that you have indeed the disease. So that's true positive. How about this one? True negative. So it means the number of patients that were tested negative and were actually negative for the disease. So it simply means you don't have the disease and your laboratory result showed that you are indeed free or negative for that particular disease. How about this one? False positive. It means the number of patients that were tested positive but were actually negative for the disease. So what does it mean? So to make it clear, false positive means you do not have the disease, or your diagnosis is you are negative for a particular disease, but the result shows that you are positive for the disease. So that is for false positive. How about false negative? It's the number of patients that were tested negative but were actually positive for the disease. So that means you have the disease. Your doctor diagnosed you with that disease, but your lab results showed that you don't have a disease. That's why it's called as false negative. So let's have here some examples. So you tell me if it is true positive, true negative, or false negative or false positive. Number 1. Glucose result is above the reference range and the patient has DM, or what we call as the diabetes mellitus. So what is this one? This is a type of true positive because the patient has diabetes. And also, the results show that the glucose is increased. So that means the patient is diagnosed as positive. So the lab results showed that the patient is indeed positive for DM because of high glucose level. How about number 2? Glucose results above reference range and the patients are diagnosed to have no DM. So what is this one? This is a false positive. Why false positive? Because the patients don't have diabetes mellitus. But how come the results showed that the glucose is increased? So that is not a true positive because the patients don't have the disease. That's why we designate it as false positive. How about number 3? Glucose results are within reference range and the patients are diagnosed to have no DM. So still, the patients don't have diabetes mellitus. And the glucose results are within reference range, or let's say the result is normal. So what is this situation? This is a true negative because the patients don't have the disease and the results showed that the patients have normal glucose, which means the patients don't have diabetes mellitus. Lastly, number 4. Glucose results are within the reference range, and the patients are diagnosed to have DM. So this is the diagnosis. The patients have diabetes mellitus. But then the results showed that the glucose is normal. So what is this? This is a false negative. False negative because the patient is actually having diabetes mellitus, but the result is normal or within reference range. So I hope you understand the terms when we say true positive or negative, or false positive and false negative. Let's differentiate analytical sensitivity and analytical specificity. First, analytical sensitivity refers to the ability of an analytical method to measure the smallest concentration of the analyte of interest. So first, what are analytes? So when we say analytes, these are substances that we detect or measure in the laboratory. So let's say you want to measure glucose or proteins, uric acid, creatinine, and vitamins or drugs. So those substances, we refer them as analytes. Going back, let's have analytical sensitivity. So when we say analytical sensitivity, it means your machine could measure even the smallest concentration of the substances in the patient's sample. So no matter how little or how low the concentration of the analyte in the patient's sample, your machine can still detect it. For example, you have a blood glucose level of 18 milligrams per DL. So this blood glucose level is very low that sometimes the machine cannot measure or detect it. That's why we can see floggings in the machine. For example, the sensitivity of your machine can only measure up to 25 milligrams per DL. So the machine will not detect the blood glucose level of 18 because it is not that sensitive enough. But if the sensitivity of your machine, for example, can detect up to 10 milligrams per DL glucose, then what will happen is the 18 milligrams per DL of glucose can be measured because your machine is sensitive enough that it could even measure as little as 10 milligrams per DL glucose. So that's for analytical sensitivity. How about for analytical specificity? So analytical specificity refers to the ability of an analytical method to measure only the analyte of interest. So this means that your machine will only detect what you want to measure, or it's the ability of your machine or your method to detect only the substance or the analyte that you want to measure. So for example, you only want to measure the glucose level of the patient. So if your machine is not specific, it could measure other sugars such as fructose, sucrose, or maltose, for example. But if your machine is having a high specificity, then it will only measure glucose and nothing else. So that is what it means when we say analytical specificity. Now let's apply the terms sensitivity and specificity for the screening and diagnosis of the patient's condition. First, we have the term sensitivity. It refers to the percentage of patients with the disease that receive a positive result. So that means the patient is diagnosed with a particular disease and the result in the laboratory showed that the patient is indeed positive. So this is a true positive rate. Next one, it also refers to the percentage chance that the test will correctly identify a person who actually has the disease. So this means that the patient is diagnosed with a particular disease and that your machine or method is sensitive enough to detect the analyte in the sample and tell that the patient is indeed positive for the disease. So it's the ability of a test to correctly identify those with the disease. So again, that is a true positive rate when we say sensitivity. How about specificity? Specificity refers to the percentage of patients without the disease that receive a negative result, and also the percentage chance that the test will correctly identify a person who is disease-free. So that means it's the ability of the test to correctly identify those without the disease. So it's the true negative rate. And you have here the formula for sensitivity and specificity. Now let's differentiate accuracy and precision. First, accuracy. It is the degree of agreement between a measured value and a true or consensus value. So take note of the words. First, we have the true or consensus value. So this is our target value. So when we say target value, that is the value that we want to achieve in a measurement. But when we say measured value, this is the value that we get out of a measurement, or this is the value that we obtain when we are measuring something. That's why it is called as the obtained value. So when we say accuracy, it is the closeness or the nearness of the obtained value to your target value. And it also refers to the veracity or the truthfulness of your result. That's your accuracy. How about your precision? So precision refers to the agreement between replicate measurements. So you are measuring something. You have obtained values during repeated measurements. So when we say precision, it's the nearness of the obtained values to each other. So regardless how many times you repeat the measurement using the same sample, for example, you will get the same values, or the values that you obtain are close to each other. So that's why your precision, it's also the degree of repeatability or the degree of reproducibility. That's your precision. So what is the goal of quality control? So the goal of quality control is for us to have reliability. So when we say reliability, that means you maintain accuracy and precision in your laboratory over extended period of time. So it's not only enough that you have precision or you have accuracy. You should achieve a high level of both precision and accuracy. That's to say that your laboratory is in quality. That's to say that the results or the data that you are releasing are really reliable and truthful. Let me have some examples so you will easily understand the difference between accuracy and precision. So again, when we say accuracy, it's the nearness or closeness of the obtained values to your target value. So for example, you have a 20-item quiz and the passing is 18. So the target value is 20. So you need to have a perfect score or a passing score for you to say that there is accuracy in your answer. For example, you get a score of 18. Then you have accuracy in your answer because 18 is near to the target value, which is 20. What about if you get 19? So it's closer to the target value. It's closer to 20. Then your answers are more accurate. But if you only get 15 or 12, for example, or 16, then that scores are not near to the target value, so your answers in your quiz are not that accurate. So that is to simplify accuracy. How about precision? Again, precision is the nearness or closeness of the obtained values to each other. So it's the degree of repeatability. For example, you have again a 20-item quiz and still the passing is 18. And your teacher said she will give 2 chances for those who did not pass the quiz. So your first score is 15. So you have here 15. So you did not pass the quiz. So for the second and third quiz, you got 14. And then another one, you have 16. So are your scores near to each other? Of course, yes. So that means the obtained values are near to each other, so there is precision. But are these scores accurate? Of course not, because 14, 15, and 16 are not close to your target value, which is 20. Take a look at this figure. Can you see accuracy here? Are the obtained values in yellow close to your target value? Of course, yes. But are the obtained values near to each other? So this is a data showing only accurate but then imprecise results. How about this one? Are the obtained values close to your target value? Are the obtained values near to each other? So this data suggests only precise but inaccurate results. How about this one? So this figure shows no accuracy and no precision. So what we need to have in the clinical chemistry laboratory is that we need to have both accuracy and precision. That's to ensure that the data that we are releasing are reliable and that we are maintaining quality in our laboratory. So let's apply the principles of descriptive statistics in examining and describing laboratory data. We have the measures of center, the spread, and shape. So first, we have the measures of centers. The three most commonly used descriptions of the center of a data set are the mean, median, and mode. So for the mean, we call it the average, and this is the most commonly used measurement of the center. And next one, we have the median, which is the middle point of the data, and this is often used for skewed data. So later, you will know what is this skewed data. Next one, we have the mode, which is rarely used as a measure of the data center, but is more often used to describe data that seem to have two centers. So we call it as bimodal. So now let's have examples on how to get the median. So again, the median is the middle of the data after the data have been rank ordered. So in short, it is the value that divides the data in half. So to determine the median, we have first to rank order the values from least to greatest, and the middle value is the median. So for example, number 1, we have first to rank it from least to greatest, and we will find the median. So in this case, we have 7 numbers. So the median data is the number 5. It's the one that divides the data in half. Next one, for number 2. So we only have 6 numbers. So we rank order this one. So it will be 4, 5, 6, 7, 8, and 9. And we have 2 medians. So to get the median, for even numbers, we just have to add 6 and 7. So that gives us 13. So we divide it by 2. That gives us 6.5. So this is now the median. How about for the mode? So the mode is the most frequently occurring value in a data set. So for example, number 1, which is the most frequently occurring value. So we have 5. So the mode is 5. How about for number 2? We have 2 modes here, the 5 and 9. So we have 5 and 9. After describing the center of the data set, it is very useful to indicate how the data are distributed. So we have now the measures of shape and the measure of spread. So the spread represents the relationship of all the data points to the mean. So we have 3 most commonly used measure of spread. So first, we have the range, then we have the standard deviation, and we have the coefficient of variation. Now we have this Gaussian distribution curve. This is the normal distribution curve, and it was introduced to us by Johann Carl F. Gauss. And as what you could observe in the illustration, it is bell-shaped. And this could help us determine or know the reference values of the data that we are measuring. So when we say normal value or reference range, that refers to the values or range of values one would expect in a defined population with no apparent clinical problems. So to apply the reference range, we have first to know the distribution of data in a normal distribution curve. So for a normal distribution curve, the total area under this curve is 1 or 100%. And much of the area, around 68.3%, is under the normal curve between the positive 1 SD and the negative 1 SD. So this is your plus minus 1 SD. And most of the area, which is 95.4% under the normal curve, is between your 2 SD. And then, almost all of the area, around 99.7% under the normal curve, is between your plus minus 3 SD. And another one. So this is your first SD. So this is your plus minus 1 SD, which represents 68.3%. Next one, you have here the 2 SD. This represents how many percent? So this represents 95.4%. And lastly, we have the 3 SD. This represents now the 99.7%. So talking about skew data. So again, when we say skew data, that refers to data that are having a long tail on one side or another. So like in this illustration, first we have the negative skew. So as what you can notice, it's called as a negative skew because the long tail is on the negative side of the peak. So also the mean is on the negative side or on the left-hand side of the peak. That's why it's a negative skewed data. For positive skewed data, we have here the long tail is found on the positive side of the peak, and also the mean is on the positive side of the peak. And we also refer it as skewed to the right because again, the long tail and the mean are all placed on the right side of the peak. Whereas at the center, that is where we can see the normal distribution curve, which is not skewed. And as what you can notice, it is perfectly symmetrical and the mean is located exactly at the peak. How about this one? This is an example of income distribution. So what type of skew data is this one? So this is a positively skewed data because again, you have here the peak and the long tail is located at the positive side or the right side of the peak, and also the mean is on the right side of the peak. So let's have the different formula that we will be using in order to determine the reference ranges of the values for our data set. So first, we have for the mean, it's the summation of x over n. And also, we have for the standard deviation. So we have here the sum of the squares of the differences between individual QC values and then the mean over n minus 1. So the standard deviation also reflects your precision because it could provide the laboratory an estimate of test's consistency at specific concentration. Like for example, you will know that the repeatability of a test is consistent because what will happen is you will get a low standard deviation, which could also mean low imprecision. But if the repeatability of a test is inconsistent, so what you will be getting is a high standard deviation, which also means high imprecision. So that's for your standard deviation. Another thing you have for the CV or the coefficient of variation, it is SD multiplied by 100 divided by the mean. So your CV is monitored in order to assess also the consistency of the precision of an assay. So for example, you have here the test A and the test B. And the CV value of test A is 17.03%. And then you have for the test B, 28.35%. So between the two tests, which do you think has better precision? Since your CV reflects your precision. So, the lower the CV, the better the precision of an assay. So this means that test A has better precision, has lower variability of values as compared to your test B. This table shows the different control values that were obtained for 10 consecutive days. And in order for us to get the reference ranges of these control values, we need first to compute for the mean and then the SD. And of course, to determine the precision of the assay, we also need to get the CV value. So first, in order to get the mean, we have the formula summation of x over n. So the summation of these 10 values is 180.2 divided by the 10 values. So that gives us a mean of 18.02 or simply 18. And after that, we need to get the difference of each x value and the mean. So like for example, in day 1, we have a control value of 18. So we have to get the difference of it from your mean. So 18 minus 18, that would give us 0. Next one, 18.1 minus 18, that would give us 0.1. And then we have 0.2, 0.1, we have 0, 0.2, 0.1, also 0, and then 0.2 and 0.1. Next one, we just have to get the square of this difference. So for day 1, for example, we have 0. And for day 2, 0.1 squared, you have 0.01, you have 0.04, 0.01, you have 0, and then 0.04, and then 0.01, you also have 0, and then 0.04 and 0.01. Next one, you just have to get the summation of this squared value. So you get 0.16. So you need this later for the computation of your standard deviation. So after plotting the values in the table, we can now get the reference ranges based on the first, second, and third SD. So again, our mean is the summation of x over n. So that would give us 180.2 divided by 10. So our mean again is 18. And for our SD, we have here the square root of the summation of the difference of your x and the mean, and you square it, divided by n minus 1. So we have the square root of 0.16 divided by 9. So that would give us an SD of 0.13. So to get the first SD, we have here the formula, the mean plus minus first SD. So that would give us 18 plus minus 0.13. So the range of values for the first SD is 17.9, which is 18 minus 0.13. So that's 17.9 up to 18.1. So that comes from 18 plus 0.13. So this is the range of values for the first SD. For the second SD, we have the mean plus minus second SD. So that would give us 18 plus minus 2 times 0.13. So that is 18 plus minus 0.26. So the range of values for the second SD is 17.7 up to 18.3. So this is for our second SD. How about for our third SD? So for our third SD, we have here 18 plus minus 3 multiplied by 13. So that would give us 18 plus minus 0.39. So the range of values for the third SD is 17.6 up to 18.4. So that means that under the Gaussian curve, much of the area in the first SD would be 68.3%. So this is the 68.3%. Next one, for the second SD, it represents the 95.4%. And lastly, for the third SD, it represents the 99.7%. So that's how we get the reference ranges and the SD values. So after we determine the different ranges of the values for each SD, we can now plot this in a Gaussian curve. So that's to visualize or to see how the values are spreading in a Gaussian distribution curve. So again, our first SD is 17.9 to 18.1, and we have the second SD, which is 17.7 up to 18.3, and lastly, we have 17.6 to 18.4 for our third SD. So to plot these values, you can do this manually using a graphing paper, or for example, you can also use your computer for this one. So first, we have, for the first SD, we have 17.9 up to 18.1. So these values represent the 68.3%. So this is your first SD. And for the second SD, you have 17.7 up to 18.3. So this second SD will now represent the 95.4% of the area. And lastly, we have the third SD, which is 17.6 up to 18.4. So this one, this will be your third SD. And again, this will represent 99.7% of the curve. So that's how you plot it in a Gaussian curve in order for you to see the spread of the values. Now we have the groups of paired observations. So even though in the laboratory, we could use the basic descriptive statistics for examining a single method, just like what we did earlier, in the laboratory, we frequently need to compare two different methods. So this is commonly encountered in comparison of methods, or what we call as the COM experiment. So in the COM experiment, this involves measuring patient specimens by using two methods. That's why we have here paired observations. So we use the existing or reference method to measure the patient specimen and compare it with a new or a test method. And the difference between the two is obtained, and that is what we call as the error. So the data obtained from the comparison of methods can be visualized graphically, and this is how it would look like when we are using the linear regression equation. So by convention, the values obtained by the reference method are plotted on the x-axis, and the values obtained by the test method are plotted on the y-axis. Another thing that we need to consider here is the correlation coefficient. This is the R value. So this correlation coefficient is a measure of strength of the relationship between the two methods, the reference and the test methods. And the correlation coefficient can have values from -1 to +1. So the signs here only indicates the direction of the relationship between the two variables or the two methods. So if you see a positive R value, that indicates that both method increase and decrease together, whereas a negative R value indicates that as one variable or as one method increases, the other decreases. How about if we have an R value of 0? So this R value of 0 indicates no relationship. Whereas if we have an R value of 1, this is what we call as the perfect relationship. So these figures show the dispersion of values in a linear regression, and it could also indicate the association or strength of relationship between the two variables. So in this case, we are using the two methods, the reference method and the test method. So again, the signs here, the positive and the negative sign, only indicates the direction of the relationship. So if we have positive R values, that means when one of the variables increases, then the other variable also increases. But for the negative value, if one variable increases, then the other variable decreases. So if we have an R value of 1, this is considered as a perfect association. So that means there is a perfect agreement between the test and the comparative method. But if we have this 0.75 to 0.1, that is considered an association which is strong. And we have 0.5 to 0.75, that is moderate association. And the next one, we have 0.25 and 0.5, that is a weak association. So in some clinical chemistry laboratory, when we have an R value of 0.95, this is already considered as excellent. So that means they are already considering that there is an excellent agreement between the test and the comparative method. But most clinical chemistry comparisons, they require that we should have a correlation coefficient greater than 0.98 to say that the reference method is comparable to the test method. Again, the difference between the test and the reference method is what we call as the error. So we have two types, the random and the systematic errors. So first, for the random error. So this is calculated as the standard deviation of the points about the regression line. So this is your standard error of the estimate. So if the points were perfectly in line with this regression line, then you will get an SYX of 0. So that means there is no random error. But in this case, we have an SYX of 5. So a random error is present. So what does it mean when we say a high standard error of estimate? So if we have a high SYX, that only means that we have a wider scatter of points from the regression line, and also there is a high amount of random error. So that's for your random error. Next one, we have the systematic error. So you have two types, the constant systematic error and the proportional systematic error. So your constant systematic error exists when there is a continual difference between the test and the reference method values regardless of the concentration. So regardless of concentration, you can see the differences in these methods. Whereas for proportional systematic error, it exists when the differences between the test method and comparative method are proportional to the analyte concentration. Thus, it is called proportional error. And you will have a clue if the proportional error exists because the slope is equal to 1. So in this case, you have 0.89. So that means there is a presence of proportional systematic error. So after determining the differences and agreement between the test and reference methods, we can now check if the new method can be used to generate reliable laboratory results. So the process is what we call as the method evaluation. So this method evaluation is used to verify the acceptability of the new methods prior to reporting patient results. So that means before we use the new method that we are testing, we need to verify it first if it can really provide us reliable and accurate laboratory data. So to maximize also the usefulness of a test, so a method is selected. So this time, this new method is selected and it will be evaluated for its usefulness to those who will be using the test, especially medical technologists. So this process is carefully undertaken to produce results within medically acceptable error to help, of course, the doctors maximally benefit their patients. For the regulatory aspects of method evaluation, we have two primary government agencies that influence laboratory testing methods. First, we have the CMS, the Centers for Medicare and Medicaid Services, which regulates the clinical laboratory improvement amendments. Next one, we have the U.S. Food and Drug Administration, which regulates laboratory instruments and reagents. So for diagnostic tests, specifically, we have the OIVD, and we have three types of diagnostic tests. So for the waved test, these are cleared by the FDA to be simple. So that means they are most likely accurate and would pose negligible risk or harm to the patient if not performed correctly. So examples of this wave test are the dipstick test, and we have your glucose monitoring. Also, for the automated methods, they are usually rated as moderate complexity. And the manual and the methods which require more interpretation, they are usually rated as high complexity. So what does the CLIA require? So the final rule of the CLIA requires that wave test should simply follow the manufacturer's instructions. So as long as you know how to perform it, you perform it accurately, and you follow the manufacturer's instruction, then it is considered as a wave test. But for moderate and high complexity tests, then they should be validated whether they are FDA approved or not. These are the general CLIA regulations of method validation. Again, for the wave test, since they are simple and most likely accurate, they just have to simply follow the manufacturer's instruction. But for the FDA-approved non-wave test, they must undergo a shorter validation process. And a more extensive process is required for tests developed by laboratories. So for non-waved FDA-approved test, you have to demonstrate test performance comparable to that established by the manufacturer by measuring accuracy, precision, and the range. And also, you have to get the reference values appropriate for patient population. Whereas for non-waved FDA-approved test developed or modified by the laboratory, you have to determine the following in order to pass the general criteria of CLIA for method validation. This figure shows the flow of procedures that need to be carried out for method validation. So as discussed, we need first to compare the new method and the reference method, right? And if we found out that the new method is at par or better than the reference method, we can now validate the new method. But then, this process is labor-intensive. It is so costly. So why select a new method? So we have several reasons. And the first one is, of course, to reduce the cost of the reagents, of the materials, of the equipment, or even the cost of the test itself. Also, we need to increase the satisfaction of our client, of our patients. And also, we need to increase our efficiency as medical technologists working in the clinical laboratory. And the most important thing is we need to improve the quality. So these are the reasons why we need to have a new method and also to validate it. Next one, for method validation, it's not only enough to get the precision, accuracy, or the range of values. It's also important that we get data from our colleagues, from scientific presentations, researches, or scientific literature. And another thing, we also have to consider the volume of the specimen. Okay, the disposal needs, the PPE requirements, the safety considerations, and of course, the personnel requirements. And of course, the test performed in a new method should meet the criteria for quality. And next one, if we have already tested everything, that's the time we can only implement the method and perform our routine clinical testing. And of course, we need to monitor our performance daily. So we need to perform quality control before we release our result. And if our results are not in quality, we need to go back to adjusting and maintaining the procedure to make sure that everything is accurate and reliable. So these are the references. That ends my discussion. Thank you.